Good afternoon, and welcome to the Masters of Reliability webinar series, Most Common Causes of Splice and Termination Failures. My name is Tanya, and I'm the Senior Learning Strategist at Novinium, and I'll be your moderator for today's session. So here's how our agenda looks today. We will go through a few housekeeping tips. I will introduce your presenter for this session, and he will cover understanding how accessories work, the important considerations necessary for reliability. He will show examples of failures, and then he'll provide a few takeaways. We'll open up for Q&A and pretty much summarize our session at that point. Okay, so that being said, I would like to introduce to you our virtual instructor, Bill Taylor. Bill is a Senior Product Development Specialist with 3M. Please take a few moments to read over Bill's credentials. And at this time, I'm going to actually hand it over to Bill.
Thank you, Tanya. So what we're going to do here is proceed with the presentation. And upon completion of this, what we're hoping to get through is that you'll be able to understand the requirements of accessory reliability and identify the common causes and list the methods, help reduce or eliminate those causes. So once you understand the basics of it and you recognize what those root causes are of many of the failures, we're thinking that you'll be able to eliminate them and greatly reduce the failures that you see in your system. So that's our objectives for this. As Tanya said, we're divided up into 3 sections. So we're going to talk about how accessories work first so you can understand that. At the end of each section, we will open it up for questions. So feel free to ask. It's an open discussion. We want everybody to ask any questions they have because we want everybody to understand when we're finished. So what I'm going to do at the beginning is discuss some basic cable theory and expand that to the accessory theory. Because if you understand the theory of how the cable works, how the accessories work, where the highest electrical stress areas are, then you better understand what's critical in the installation of the accessories and why the cable preparation is critical, and can therefore incorporate those into the design and into the installation to make sure you have a very reliable system. So we're going to start with electrical stress theory on the cable. And this is a typical insulated power cable, shielded power cable, where you have your conductor, your insulation, and your insulation shield on the outside. Whenever you go to splice or terminate this cable, you obviously have to remove some of that insulation shield, because you can't just have ground here and high voltage on your conductor and ground on if your shield ended here, insulation shield, because a 15 kV, 175 mil cable, 175 mils of distance is not enough to insulate and to keep it from flashing over that higher voltage. So you remove the semicon back to this point, but when you remove it or terminate in that shield, you can see that your equipotential lines in your cable tend to get very close together at the end of that shield. And the closer those equipotential lines are together, the higher the electrical stress you have. So what we do with accessories is they overcome that high concentration of electrical stress at the end of that insulation shield on the cable. And we will discuss then these equipotential lines and the flux lines and how those work together as we get into the discussion of the electrical stress. So we have this electrical stress. Why does it occur? How do we control it? So let's look at shielded power cable theory briefly. This is a typical power cable and the components of it. We'll talk briefly about each of the components. So you have the conductor and the conductor shield. and then the insulation, which insulates the high voltage on your conductor from ground on the outside, which consists of your semiconductive insulation layer of the insulation shield and the metallic. So your insulation shield is comprised of both of those layers, the semicon and the metallic. And then you have a jacket on, typically on the outside of the cable. So let's look a little briefly at the common cables that you see out there. Tape shield is very common, been around forever. It's used mostly in industrials, but some in network in the splices. Have wire shield, which is more common in Europe, but also used in industrial applications, as is unishield, typical industrial. And you have some PILC in both utility and industrial applications. More common utility cables are your concentric neutral, which most are jacketed concentric neutral now. You have a jacket over your neutrals, or you have a longitudinally corrugated type of shield on the metallic. From the conductor standpoint, so we're going to start on the inside of the cable and work out. Let's talk about the conductors briefly. Typically copper or aluminum. Copper is typically used by industrials, and it has more conductivity than aluminum, therefore you can carry more current on copper. It also thermally expands and contracts less than aluminum, so therefore connectivity to it is more reliable or less susceptible to installer error. Copper is than aluminum. So aluminum is typically used by utilities because it's lighter in weight, and therefore they're running miles and miles of cable. You want something that's lighter. Does carry less current. The other issues with it is you tend to get oxidation on the surface, and that oxidation that forms alumina oxide, which is an insulator, and you have to break that down when you connect to the connector. And again, its thermal expansion is greater than copper, so it expands and contracts more, and therefore tends to work the connector loose if it is not installed properly. So it has less installer error on aluminum than you do on copper. And your conductors, there are multiple ways of doing these. You have fine strand flexible, which is used for locomotive or welding cable, or mining cable. Concentric strand are compressed. Most of your power cable is going to be either compressed or compact stranded, with some of the smaller sizes being solid. But compressed is 97% of concentric. Compact is typically 91% of the diameter of concentric stranding. Okay, so what purpose does the strand shield serve around the conductor? If you look at the picture on the left, where you have your conductor, your round strands do not mesh all together, as you can see, and so you have pockets of air inside between them and on the outside. Well, on the outside, if you put the insulation there, you're going to have a potential difference from the valley of that triangle, where that air gap is between the conductors, where they come together, to the outside. And that potential difference can cause air to ionize and cause corona discharges or partial discharges in that area, which can eventually break down the insulation and cause a failure. So what the strand shielding does is it fills in those air gaps around the strands, conductor strands, and gives you a nice smooth surface for the insulation to bond to, and so that there's no air voids between the insulation of the cable and the high voltage conductor strands on the inside. And therefore, with no air voids, you eliminate the potential discharges, or the partial discharges that occur at that interface. So your insulation is next on your cable. Different types of insulations are available. PILC has been around forever, paper insulated, oil impregnated paper with a lead jacket. And Typically, all of these cables are normal operating temperatures are 90 degrees C. You have cross-linked polyethylene or XLPE, ethylene propylene rubber, which can have a 90-degree operating conductor temperature rating or a 105 C rating. Typically, for PILC, the emergency overload temperature is lower than it is for cross-linked polyethylene or EPR. So you can only overload PILC to 110 conductor temperature, whereas cross-linked polyethylene and EPR rubber, you can overload to 130 C, or in some cases 140 C if it's a 105 continuous rating. And typically that emergency overload rating, you're only allowed to run it for a maximum of 1,500 hours for the life of the cable. If you run it longer than that, which you can and does happen, what happens is basically you're reducing the life of the cable because the temperature or thermal will degrade most materials. The longer you run it at a higher temperature, basically the shorter the life will be. So what you're doing when you run it at longer than those 1,500 hours is you're basically reducing the life of the cable insulation. And the cable insulation level is basically determined by the connection of the transformers feeding that system. So typically 100, if you're going to clear a fault current real rapidly, and most of our systems here are hard grounded Y systems, which will clear the fault very quickly, depending on the breakers, fuses, whatever you have in front of it. It will clear typically in 6 cycles or less. And in that case, 100% level insulation is recommended. If you're going to leave the fault current on for longer than a minute up to an hour, it's recommended that you have 133% insulation. Or if you're going to use an ungrounded delta type configuration on the transformer where you can have phase-to-phase voltage on the phase-to-ground system indefinitely, then it's recommended that you use 173% insulation level so that it can handle that phase-to-phase voltage on the phase-to-ground system. Most utilities use 100% level cable insulation. Most industrials use 133% level. Even if they have a hard grounded Y or high resistance grounded Y, they use 133% level just as extra security to improve their reliability as well. Okay. So let's look at what happens if you have a non-shielded cable insulation versus a shielded power cable. So we're talking about the insulation. What happens if you have a non-shielded cable, you pull the insulation into a conduit or lay it up against a building where it is in contact with ground. So you'll see that it's in contact with ground in this specific area. Well, what happens to these flux lines is they then are concentrating and more going towards ground, and they're getting concentrated in that area. So you have a high stress concentration where that cable insulation is touching ground. And so therefore, with a non-shielded power cable, you have to have a significantly thicker insulation level in order to handle that. Typically 5 kV non-shielded power cable has 140 mils of insulation for a non-shielded and 110 mils for a shielded power cable. Likewise, one utility dug up some non-shielded 15 kV power cable, and it had an insulation thickness of 345 mils, which is a 100% level for a 35 kV cable, but that's the insulation level it needed in order to operate as a non-shielded power cable at 15 kV. So you can see it's significantly more insulation with a non-shielded cable because you have that local high concentration of stress. Whereas if you look at a shielded power cable, then it gives you ground potential on the outside of the insulation, so therefore you get uniform flux lines. So your field distribution is very even and very uniform in the power cable, and therefore you can reduce the insulation thickness in that cable. Your equal potential lines in a power cable look like this, and these are just the voltage that you have remaining from the conductor where you have high voltage to ground on the outside. So 80% equal potential line means you have 80% of the voltage occurs at that location. So if you have a 7200 volt phase to ground system, which is a 12470, you'll have 80% of that 7200 volts at this location, 20% here, and of course 0 on the outside because it's at ground potential. So you can see that the equal potential lines are closer together near the conductor, and the closer together the equal potential lines are, the higher the electrical stress at that particular location. And then your flux lines, they're perpendicular to your equal potential lines, and so you can see again uniform, even field distribution when you have a shielded power cable. And that's what your Semicon does on the outside of the insulation, provides that ground. And again, it provides, since it's extruded onto the insulation and semi-bonded to it, or bonded to it, depending on your type of cable, you have a nice smooth surface on your insulation, nice smooth surface on the inside of your Semicon, and therefore you have no air voids between the grounded Semicon or grounded insulation shield and the cable insulation itself, and therefore no air voids to ionize or go into partial discharge. Okay. And as I said, your insulation shield consists of two components, the Semicon and the metallic shield. And the metallic serves numerous functions. Again, ensures that your Semicon remains at ground potential. And in the case of neutral wires, carries the neutral current back. Also can carry the short circuit current. If you have a tape shield type design, you're going to carry a separate ground wire that will designed to carry the fault current. And so these are the functions of your metallic grounds, depending on whether it's set up as a JCN cable or a tape shield. Some of the functions are exactly the same. But your tape shield will not carry as much current as your neutral, so therefore you carry a separate ground with it. And of course your jacket on the outside is there to provide physical protection, and very common rubber, PVC, high-density polyethylene, many different kinds of jackets that provide that physical protection for your cable. Okay, so now that we've looked at cable theory briefly, let's look at how that relates to cable accessory theory. So again, if we look at the electrical stress plot of removing the Semicon, or the insulation shield level on the cable, and we can see how all the equal potential lines, flux lines, tend to concentrate near the end of that Semicon, so you get a very high electrical stress at that point. So let's look at how we control that stress, and in order to do that, we need to know what that stress is a function of. And again, it's a function of the voltage that you have on the system, whether you have it's a 15 kV system, 25, 35, or higher. The higher the voltage is applied, of course, the higher the electrical stress will be. It's also a function of the thickness of the dielectric or insulating materials on the surface. So your cable insulation is your dielectric insulation on your cable, and that thickness increases as your voltage goes up. And then the properties of that dielectric material. How good of an electrical insulator is it? What is the dielectric strength of the material? Those things play into it. And the geometry, or basically the distance between the components, how they're configured, whether they're in a geometric shape or just tubes are just straight lines between them, and the distance between high voltage and ground, which are the electrodes we're talking about here. So the distance between them makes a big difference as well. So you have a lot of things that go into determining the electrical stress in your accessory. And then, so let's look at how we control that stress with a termination first, and then with a joint. So with a termination, what you're doing, the definition of it is that it ends or discontinues to end the insulation shield on the cable. So it ends the insulation shield or stops it, and that basically terminates the shield on the power cable. So as we saw from the previous slide, when you terminate that insulation shield, your stress concentration is very high at that shield. So one way of controlling that is with a geometric stress cone. And I'm going to use the picture because it's easier to explain how that works. But with a geometric stress cone, what you do is gradually increase the insulation thickness from the end of the insulation shield, where you terminated that insulation shield, and you gradually increase that insulation thickness up to a point, and then gradually ramp it down on the other side back to the insulation. What that does is that adds extra insulation to the cable insulation, and it moves the high stress point. Then you also extend the insulation shield up to the peak of that insulation that you've added, and then that transfers the high stress to the end of that insulation shield that you now have at the peak of your added insulation. So now you have the cable insulation plus the additional insulation from the geometric stress cone to overcome that high stress. So even though your electrical equipotential lines are very close together still, and you still have a high electrical stress here, you overcome that high stress with extra insulation, and instead of some other method. So that's why it's called geometric stress cones, and that's why people call termination stress cones from that geometric stress cone terminology. The way most medium voltage terminations control electrical stress nowadays is with high dielectric stress control, or high K material. And the way that works is it's similar to the way water refracts light. So if you look at something underwater, it looks like, and you reach your hand in, a lot of times you miss it because it actually looks like it's in one place, but it's in another because the light is refracted, which shifts the image. And the high dielectric stress control works the same way with the equipotential lines. It shifts them so that they're no longer concentrated at one place. And the way that works is you have two dielectric materials, and dielectric constant is signified by the letter K. And so your dielectric K value is your insulating ability of the material. And your dielectric constants start at 1, which is the dielectric constant of air, and everything is relative to that dielectric constant of air. So the higher the dielectric constant is, the less insulating ability the material has. So when you get to an infinite dielectric constant, you have a semiconductive material or a conductive material because it has no electrical insulating ability. So the insulation, the dielectric constant of your cable insulation, like cross-linked polyethylene is 2.5 to 3 typically is your dielectric constant. Ethylene propylene rubber typically 3 to 3.5. And so what we do is with the high dielectric stress control material, you want it to have a dielectric constant that's higher than that, significantly higher than that. So maybe in the order of 20 to 30 typically. And when you do that, so you have this dielectric constant material here, which is your stress control material, and has a dielectric constant of around 20, say 25, and then your K value of your cable insulation here. Well, you can see when that happens, these equal potential lines are refracted out. They're spread out, they're refracted, so that now you have lower electrical stress at your semicon step, so therefore it won't go into partial discharges readily, and you have lower stress on the surface of your termination because that electrical stress is spread out instead of being concentrated on the surface of your termination. So what that means is that you can have a shorter termination, a lower profile, smaller profile, shorter, because you have that lower surface stress. So therefore, you can get the same performance out of a shorter termination because you have lower electrical stress. With lower electrical stress on the surface, you also have less chance of tracking. Reduces the risk of tracking and other issues with the termination. The challenges with high dielectric stress control is you have dielectric heating, and you have lower dielectric strength of the material, and also DC stress control is more challenging. And we'll talk a little bit more about dielectric heating in a bit. This just kind of is the comparison between the two. So your high dielectric stress control term is on the right, and you can see it's much shorter than your geometric cone. With your geometric cone, you still have 80% of your electrical stress in a very short distance, so you have very high surface stress. So therefore, you need a much more distance from your high voltage lug to the ground at the base of the termination in order to meet the test requirements and to keep it from flashing over. Whereas because your stress is spread out more here, you have lower surface stress the whole way, therefore can meet the performance test requirements and get better field performance with a shorter termination because of that lower surface stress. Therefore, not flashing over, not breaking the air out around it as readily because it has lower stress there. All right, so let's look at joints now that we've looked at terminations. And most of your push-on joints, your Epdm, some of your cold shrink joints use geometric stress control, just like the geometric terminations that were originally there. And the difference is that with a joint, you're taking those equal potential lines that are running through the cable insulation, you're bending them and forcing them into the joint insulation and then back into the cable on the other side. Whereas if you looked at the termination, these equal potential lines come out of the termination into the air, so air is part of your insulation with terminations. With joints, that's not necessarily true because you're containing all of those equal potential lines and all that electric field inside of the joint because you have insulation shield on the outside, which is that ties into your cable insulation shield, so it's at ground potential, and it keeps all of the electrical stress in the splice insulation and the cable insulation. So here with the joint, you have, when you take those equal potential lines into the joint insulation, at the electrode, which is a semiconductive element in the middle of the splice, which creates a Faraday cage, which the Faraday cage means that this electrode is the same potential as your conductor. So all the air around the connector, there's no potential difference across that, in that air around the connector. So therefore, no potential difference. There's no electrical stress, and therefore you don't ionize that air around the connector. As you can see, the equal potential lines are very close together here, so that's a very high stress point. So we analyze that, and also this is the interface between the joint insulation and the cable insulation. is typically a weak point, so we analyze the electrical stress there, and then we look at it back over the electrode here. And the object is to design these high stress points so they're lower than the max electrical stress in the cable. And again, you overcome that with, as we talked about before, geometry, distance, and the type of insulation that's used in the joint. For high dielectric stress control joints, you need actually a longer interface because, again, you're refracting out, spreading out those equal potential lines. And in order to get them spread out adequately, you need a little longer distance between your cable insulation shield and the electrode and the splice. And again, you have high stress in this area along the interface, and then looking at the cable, at the joint insulation itself over the electrode. And again, the goal is to maintain the stress lower in the joint than in the cable itself. So a summary of electrical stress in medium voltage cables. You have that stress where you terminate the shield on the cable, and you have to control it and try to minimize it. And you can control it with geometric stress control or high dielectric stress control, but you have to control it, you have to insulate it, and you have to take care of that stress. And then you want to choose the best method for your particular application. Okay, with that, we're going to open it up for questions. So, Tanya, I'll turn it back to you if you want to read the questions, and then we will answer them. Hopefully we have some.
Yes, we do. Our first question comes from Brad, who asks, do you see a preference between high K or geometric terminations?
Yes, and I'm probably partially prejudiced, but high K or high dielectric stress control terminations are pretty much dominating the market now. Almost everybody uses those, and it's for some of the things that I mentioned there, because you have a lower surface stress, and if you have a lower surface stress, you're going to have less chance for tracking on the outside of the termination, and therefore you get more reliable, longer-term performance out of the termination. So based on the better stress control that you get with high dielectric stress control, I think it makes for a better termination because of the smaller distance you can have, especially with switchgear getting smaller and smaller. It allows you to have a shorter termination in that switchgear and still have lower surface stress on the termination, which will improve the reliability. Okay, good question.
Okay, the next one comes from Daniel. He wants to know, will the dielectric heating at the stress cones show up as hot spots in infrared?
And that's another good question, and typically it can show up when you, at your semicon step with terminations, that are high dielectric stress control, especially at 35 kV system, you can have as much as 2 to 5 degrees hotter temperature at the semicon step on the surface of the termination than in the rest of the termination. So you may see that, and if you see that, that's nothing to be alarmed at. It will show up as a slight hot spot, and I have seen it show up on some infrared studies, but that's very typical to see that little bit hotter temperature there, and it doesn't affect the performance of the termination or the life of the termination. But you may see that. 15 kV, you're probably not going to see it. Probably won't show up, but as you go up in voltage to 35, it almost always shows up on the infrared scan. Okay, good question. Thanks.
Okay, the next one is from Daniel as well. What about operating temperatures, performance between silicone and Epdm? And he follows that question up with, what about birds pecking at silicone rubber?
Okay. Temperature performance, Epdm rubber versus silicone rubber. Silicone, of course, has a very good temperature characteristics, so it can withstand very high temperatures and very cold temperatures, and doesn't change its performance or doesn't affect it. It can withstand higher temperatures than Epdm, but Epdm rubber can easily withstand any of the temperatures that you see in a cable, either operating temperature or emergency overload temperature that you can see at 130 or 140 C. None of those temperatures will affect either Epdm or silicone rubber. So they're both adequate in terms of that. In terms of birds pecking silicone rubber on terminations, haven't heard of that one before, but that's an interesting question. And I guess anything that nicks or causes damage to a rubber that's expanded and under mechanical stress, which cold shrink terminations typically are, and which are your silicone on the outside. Anytime you nick that or cause in there, it can cause it to split or to cause problems because it's under mechanical tension from being stretched. So I don't know if there's a way to eliminate that or not with birds. I don't know why they would be pecking at it, but and I don't know what to do about that one. That's an interesting one. There are some kind of animal guards and protections you can use on systems, and you might want to investigate something like that if that's a perpetual problem. But like I say, I haven't heard of that problem before, but it's interesting. So thanks for asking.
Okay. So he also asks, do you commonly see ripping of the silicone rubber on cold shrink terminators at the base? If so, what causes this?
Okay. Typically, we don't. It's very uncommon to see it at the base of the termination. Occasionally, you see it at the lug end of the termination, and most often that's caused by a crimp that was put into the lug that was not filed off or became sharp edge or sharp point, and it will cut or puncture the silicone on the end and start to tear. Occasionally, I have seen it at the base, and it's what is usually causes it is when the linemen fold back the neutral wires. They may tap them with their clines to knock them down and get them to a smaller diameter. And if they do that, they can create a sharp point or edge on those neutral wires where they're tapping it. And that sharp edge can puncture through the silicone down the bottom end. But very, very seldom have I ever seen one on the bottom split, and that was determined that was the cause of it. Okay?
Okay. Now, Noel wants to know if the time to clear ground faults determines the mill's insulation selected, how does 220 mil differ from 295 mil insulation? I believe, and he says, I believe we use 100% of our calculations.
Okay. Yeah, and like I said, most utilities use 100% because typically their systems are hard-grounded Y systems, and they're going to clear the fault right away. And because they run so much cable, they don't want any extra to pay for the extra insulation that would be needed for 220 versus 175 mils for 15 kV cable. 220 mils is typically your 133% level for 15 kV cable, and 295 mils is 25 kV insulation or 28 kV cable rated insulation. Originally, 295 mils was the 100% level for 28 kV. It's now 280 mils. So if you have any 295 mil cable, it's probably relatively older cable and had that 295 mils of insulation. But typically, 25 kV cable now, 100% is 260 mils, 28 kV is 280, and the 295 is older versions of the 28 kV cable. But now it's all either 260 or 280. So hope that clarifies that up. Thanks.
Okay. Shauna wants to know, do we get a copy of the slides? And Shauna, I'll answer that question. Yes, you will be provided with a copy of the slides. Just reach out to us via email, and we'll make sure you get a copy. And it'll probably be most likely we'll have a copy of the slides on our Novinium website. The next question comes from Gail. Gail asks, how does excessive conductor temperature fail cables?
Okay, so if you get excessive temperature on your cable, like I had mentioned before, the more you heat a polymeric material, or the more temperature or the more heat it sees, it tends to degrade it more rapidly and therefore reduce the life of the cable. So if you exceed the emergency operating temperature for an extended period of time, you're going to start degrading the material and will cause it to degrade more quickly, more readily, and therefore not meet the expected life of the insulation or of the system. So temperature always excessive temperature typically always degrades polymeric materials more rapidly, and that's what reduces the life of the system. Okay, thanks.
Okay. Ken would like to know, how much tolerance do terminations and splices have for positioning over the end of the semicon on the cable?
That's a good question. It depends on the manufacturer partly. Some of us put more tolerance in than others. For our particular ones, we like to see a minimum overlap on the semicon of the stress control material of a 1/2 inch. And typically we have quite a bit of tolerance in there, usually probably 1/4 to a 1/2 inch of tolerance. We don't tell linemen that. We just, we want them to hit it exactly, so that so if they are off a little bit, you still don't have an issue. But again, it depends on the manufacturer. Some manufacture more. It also depends on the type of joint or termination. Cold shrink typically will have more tolerance built in than a push-on, because a push-on you don't have as wide of a range of conductors to cover, and therefore you're not going to have as much variation in install length. And by that, if you take a cold shrink joint, it can vary as much as 1.5 inches install length from the min to the max size conductor, just because of the laws of physics, because it's expanded significantly more. You will not get that big of a length change in a push-on because you don't expand it that much. So therefore, again, it depends on the type of accessory and the manufacturer, both of those issues. So hopefully that helps. Thanks.
It does, and I think we have time for a couple more questions. Gail also wants to know, do you have an example of the smallest type of insulation error that would cause a failure of a cable accessory at 35K? Example, how deep of a knife cut at the Semicon Spec, and how big of a Semicon tab will cause a failure? Okay.
As I mentioned, the higher you go in voltage, the less significant a defect will cause more of a problem with it. So we've done some experimenting, and I know I haven't done it exactly to see exactly what caused a failure, but I have done some with as minimum as 10 mil deep knife cut in the insulation, and even with 10 mils deep, it will fail almost immediately at 35 kV. So it takes very little depth to start the failure process at that location. And the same with the jagged semicon. It doesn't take very much of a jagged edge to initiate a sharp point and initiate high stress at that area and to cause problems. So like I say, 10 mils is not very much, and that definitely caused a problem. And it's probably a less deep knife cut than that will cause issues. So That's why cable prep is so important to reliability and to long-term performance. So thank you.
Okay. Last question here for now. If XLP has lower k, how come EPR is preferred for HV? And that comes from Sean.
Okay. In my experience, I wouldn't say that EPR is preferred for high voltage applications. A lot of your transmission cables that are insulated, shielded power cables, do have cross-link polyethylene insulation as opposed to EPR. There are a lot of 69 kV cables and higher out there that are EPR, but a significant amount are cross-link polyethylene insulation. So, and again, if you're going to go to transmission, which we're mostly talking distribution here, but you probably want a lower loss EPR, and there are lower loss formulations out there and that are used to do this. So you have less dielectric losses in those materials than you do others, but typically cross-link polyethylene has a lower dielectric losses in it than EPR, as well as a lower dielectric constant, because typically as your dielectric constant increases, so do your dielectric losses in the material, and that's why you get the dielectric heating in the stress control, high K stress control tubes or high dielectric stress control tubes, because they have more dielectric losses. So, but to answer the question, there are a lot of cables that are cross-link polyethylene, and I'd say actually probably predominantly cross-link polyethylene in high voltage versus the EPR. So anyhow, good question. All right, is that our last question you said, Tanya?
Yes, you can keep going.
All right, so all right, let's move on then with the next section of our discussion, and we'll talk about the important considerations necessary for reliability with accessories. And so, back up one, get carried away here. All right, so we're going to talk about 3 different areas in this section, and we'll go into these in a little more detail. But it's important to choose the best accessory for your application, and that includes, you have to take into account numerous things to do that, including the environment, the voltage, and a lot of other things. So we'll talk about that. Training installers is very important, and that training includes not only how to install the cable accessory, how to prep the cable, but theoretical reasons why things are important. And then it's important to follow up with them afterwards to see if you can minimize steps, make things simpler, make things easier. The fewer steps, the simpler the situation, simpler the installation, the less chance there is for error, and the more reliable your system will be. So if you're looking for choosing the best accessory, consider the following. The environment is critical. You have to consider that if you're looking for a live front termination. If you're going to put one next to a concrete plant versus out in the middle where there's in an area where there's no contamination, or if you're putting one in a coastal area versus an inland area, those things are very significant because you can have much more. You need to consider the environment, because if you're going to contaminate an environment, it's recommended that you go to a higher voltage termination in order not to have flashover, not to have reliability issues with it. And a lot of that is covered in the standard for terminations, IEEE 48. And then you want to look at an accessory with the fewest components, because the fewer steps you have, the fewer components, the less chance there is for error. And one other note about environments is if you're dealing with a joint, you want to consider whether it's going to be aerial, up in the air, or direct buried, or in a manhole. and if the manhole is full of water, and if the manhole sometimes sees hydrocarbons or not. So all of those things you have to consider and then choose the best accessory for that environment. And again, a simple installation is best because then it's going to reduce your number of steps, make things simpler, and therefore easier to install. And the easier it is to install and simpler it is, the less chance there is for error, and therefore the increased reliability. And as far as application itself, a lot of your accessories nowadays are range taking, and you really want to try to choose one that, if you have a particular cable, if it fits in the middle of an application range, that's better. Closer to the middle versus at the very low end or the very upper end. If it's the very low end, you're going to have less interface pressure between the accessory and the cable installation. And there are studies out there that show the higher the interface pressure, the better the electrical performance. If you're on the upper end, you may have clearance issues with, in terms of removing a core if it's a cold shrink device, or and that can cause issues as well. So whatever type of accessory you have, you want to fit the application best plus the other components. And you want to do a lot of training, because there are tricks in order to install all different accessories and to make sure that they're installed properly. But in addition to the training on that, you want to emphasize the theoretical aspect of it, so they understand where the high stress areas are, why cable prep is so important there to keep it from failing. And the more they understand, the more they know, the more pride they're going to take in their work, and the more they're going to want to do a good job, because everybody wants to do a good job. And the more they understand, the more it enables them to do a good job and get them installed correctly, so they will be reliable. So again, following instructions, paying attention to details, all very critical, and emphasizing why they're doing certain things so that they more likely to do them properly and as required. So a lot of different areas there that are critical. And again, emphasize to them that workmanship causes many of the accessory issues. And so it's important to take your time to do a good job, to do it correctly. More important than speed is accuracy in these, in order to get longevity and reliability out of your accessories. And these are just some of the issues that can occur. Knife cuts in the installation, which we talked about, those are bad. If you remove the wrong amount of Semicon, prep the cable incorrectly, remove too much jacket, don't have enough neutral wire to go across, or you improperly position the accessory, or you improperly install it. If you're doing cold shrink, once it's locked down onto the cable, if you push it forward or you stretch it back, you can misposition it that way. And I've seen people overlap the termination, the tubes on the termination, and therefore misposition this stress control so that it doesn't land on the end of the cable insulation shield and fail that away. Or they stretch it out way far and causes it to miss that away. So proper technique is very important. And you don't want to lift the Semicon, because that creates partial air and partial discharges. And with your connector or your lug, if you don't fully engage it into there, I'll insert it all the way in, and you're not getting the proper amount of surface area contact between your lug and connector and your cable, and therefore you can have hot spot, or you can run excessively hot because you're not transferring the current adequately. Also, when you're crimping it, you can have too few crimps, wrong guys. You can remove. A lot of people remove too much of the inhibitor. All those things can cause you major problems with your accessory and need to be addressed. So And then once you finish, you want to follow up with the installers to see if there's ways to improve, make it simple, more simple, so there's less chance for errors, and then either modify the instructions or work with them to improve those things so that you can get that reliability we're looking for. Okay. Any more questions before we move on to the last section? We just have a few more minutes here to try to finish up. So.
We do. We just have a few more moments, so I'm actually going to reserve these questions for the end if you want to keep going.
Okay. Let's do that then. Let's look at a few examples of failures, and then we'll end up with the summary section and answer any last questions. Okay, typical, this is what a ring cut looks like. You can see it on the right. These were two joints out of the same area, and you can see the cut in the insulation. You can see the hole beginning to form here, and this one it actually failed and blew a hole through the cable insulation at that particular point. This is one where the wrong kit was used. Tape shield kit was used on JCN cable. Instead of bringing the neutral wires back out of the base of the termination and connecting those to the ground, they attached a thin metal braid or thin metal strap with a constant force spring. It didn't have the ampacity necessary to make to deal with the current on the neutrals, and it didn't make a good contact, and therefore it overheated and caused the failure. So using the right kit is critical. An example of a connector that was wrongly crimped. You can see this side was crimped reasonably well. This side, they used an entirely different crimper, over-crimped it enough so that they actually broke the conductor inside because it over-crimped it so much that it thinned it out that it actually broke in two, creating a very high resistance connection and caused the failure of the system. Again, one where the termination was either not started at the correct marker, or it was stretched, or the cable was misprepped. Whichever way they did it, the stress control tube actually missed the insulation shield of the cable, the semicon of the cable, therefore creating an air void between them with no electrical stress control, and it blew a nice big hole in the cable at that end of the semicon there. So this is one where the joint was mispositioned and there was no grease in down the insulation. So you can see that the end of the joint shield didn't overlap the insulation shield of the cable, and it also will cause the electrode to miss being on the cable insulation and therefore cause it to fail. So we had tracking down the interface with no grease and no stress control because of the missed semicons and the electrode. And one last one that sometimes you have to follow directions, and when you don't, this person actually left the core inside of a termination, if you can believe it, taped both ends. Obviously no electrical stress control because the termination didn't land onto the cable itself, and so therefore it blew up it failed in the field when it was installed. So just a few examples of what can cause problems. Again, the wrong kit selection sizes can be bad. And we talked about environment and design, and then again, that's something that is very critical. In these examples, actually, you can see where the end of the termination was sealed onto the lug, that the lug is still shiny, still has the tin plating, but this is a coastal environment, and the rest of the lug is very corroded. And what happened over time is that it corroded even the inside of the pad where they're bolted together and bolted onto the bus, and because it was out in the environment, and therefore you got a high resistance contact connection, and then when you had a surge on the system, it actually jumped across the bolted connection and melted the lug barrel itself because of that corrosion on the pads of the lugs and the high resistance connection. So so there's a few examples, and just because we're about out of time, I'm going to do the quick takeaways and summaries for you. And then if anybody wants to stay on, if we have a few more questions, we can answer those. But again, the key takeaways, help the installers understand how system works and the criticality of that, and why the requirements are set, and why the instruction sheets are specific in terms of dimensions, the way things land, the way things go together. Once they understand that, they will be much more cognizant of if something is mispositioned or out of alignment, and they will say, no, this isn't right, this doesn't work, let me fix it before I just leave it like this and go on. And therefore you'll have a much more reliable system. So teaching, explaining as you're doing the training is very, very critical to the workers, as well as training them to do that correctly. And then give them examples of what happens, show them failures and the reason for the failures. Give them examples of what happens when it's not properly installed or prepared. And again, follow the critical nature, explain, emphasize the critical nature of how critical cable prep is, how important it is to follow directions so that everything lands where it's supposed to land, and make sure they understand and they check to make sure things land where they're supposed to before they leave the installation. So, and that's the end of my presentation, so hopefully that was educational for everybody. I'm going to turn it over to Tanya, and we'll go from there. Thank you all very much for attending.
Okay. I definitely want to leave you all with some next steps. First of all, yes, thank you for attending. After completing the webinar survey, we're going to send you a survey via email. You will receive a certificate of completion. Be sure to register at novinium.com for additional Masters of Reliability webinars. And there's some actual information there for the ICC that Bill can talk to you about, and his email as well for some follow-up information. So, Bill, do you want to explain the ICC website?
Yes, and ICC is a member of the IEEE, is a sub-organization of the IEEE. So you have the Power Engineering Society, and then the Insulated Conductor Committee, which is what ICC stands for, is a subcommittee of the Power Engineering Society, and it's where all we deal with is insulated power cables and accessories. So we talk about the design of, about installation, talk about all the different areas, the different types of cables, and then discuss the accessories. We write all the standards, industry standards for testing and for qualifications and for field testing, and deal with all the field testing issues that come up, and write the standards for all the different types of field test methods. So it's a very good organization, has lots of very knowledgeable people in it, and I would encourage you to attend and glean some of that knowledge from, and all of your webinar masters regularly attend the ICC and are very active members in the ICC. So there's a tremendous amount of knowledge there for you to partake of and enjoy, and help you to grow in your field. So I would encourage everyone to participate in that. Thank you.
Okay. All right. If you are okay, I think we can follow up with some additional questions. If someone needs to drop off, that's fine. We've concluded our session for today. But if you are able to stay on to Bill, is that okay for us to ask?
That's fine with me. Yes.
Okay. All right. Well, I'll go with the next question. The next question I have here is, it comes from, it comes from John. John asks, what is an acceptable temperature difference or ratio between a splice joint and the same cable carrying the same ampacity?
Mm-hmm. Carrying the same current, yes, same ampacity. And that's going to vary depending on the type of joint that's on the cable, as well as the type of cable insulation. If you have 133% insulation, your jacket temperature in your cable is going to be a little less with the same ampacity as it will with 100% insulation. You may have, if you have the same joint on both, you'll have a different temperature difference between the two. And also your joint temperature jack outer temperature is going to depend on what manufacturer joint, what kind you have, whether you have a cold shrink joint or a push-on joint, a pre-molded joint, or heat shrink. It will vary that because it will vary with the insulation thickness and the thermal conductivity of the material. Typical level, I mean, if you're very low current on there, very lightly loaded on the low end, they're both going to probably be at ambient temperature, so you wouldn't see any significant difference. As you get up in temperature, you could see as much as 10 or 15, maybe even 20 degrees, the difference in temperature between the cable jacket and the splice jacket. Again, it depends on the type of accessory that's on there. And NETRAC did a study on that. They're a test lab in Atlanta, Farmer Southern Company's test lab, and that was their conclusion, is that really the temperature difference depended on the type of accessory on the cable. So, but to give you an idea, it could be, 0 to 10 or 15 degrees C, depending on the accessory. So, thanks.
Okay, we have one from Yuri. Our majority of termination failures at Semicon overlap point due to improper insulation, or is it due to improper stripping on Semicon or on cable?
Good question. I would say probably the majority are due to the improper cable prep, and most likely not stripping off the Semicon correctly, either putting a knife cut in the insulation or something like that. We do see them where they are misapplied. I've seen terminations that were stretched out so far that the stress control tube missed entirely the cable Semicon, and that led to a failure. And as I've said, I've also seen them where people pushed them and overlapped them and caused it to miss that away. So, but the majority of them probably come from cable prep and knife cuts in there versus mispositioning of the accessory. Okay, thanks.
Okay, Rick would like to know, how important is the process of using a drain or bleed wire on EDPM products in terminating?
Okay, using a bleed wire is very important on all accessories, whether Epdm rubber or silicone rubber. For example, a cold shrink termination, live front termination, or a push-on live front termination out of Epdm, your outer housing is track resistant, and where you end the insulation shield on your cable, you're going to have leakage current coming out of your cable, and it's going to be in your termination, and that leakage current is going to go through that track resistant housing and looking for ground, and it's going to find ground. So it's important that your live front terminations have that metallic ground on the outside of them. They need to be in contact with the grounds underneath or have a bleeder wire on the outside so that they are at ground potential and that leakage current can be bled off directly to ground. If that bleeder wire is not there and it's totally insulated from ground, that leakage current will find its way to ground through whatever material is in the way, and it'll eat up that material and eventually cause you to have problems and potential failures with your system. If you're talking dead front, which we'll be talking later in one of the webinars, but there it's very important that you have that dead front, either elbow or T-body grounded, in order to ensure that it's at ground potential. Otherwise, it could be floating, which would be bad, because then it would float up with voltage on it. But it's important to have it at ground potential for that, and also to bleed off that same leakage current that's coming out of that system. So very, very important either way, and either way can lead to failures if they're not grounded, if the housings aren't grounded. Okay, thanks.
Okay. Bertie would like to know, is there a way or tool to detect a potential failing termination, And can the infrared camera pick up a potential failing termination?
Infrared typically probably will not pick up a failure. As I mentioned, you're going to have a little bit of difference in potential in temperature at the semicon step of there. What infrared can do is it really won't show you that the accessory is failing, but it can show you if you have a bad connection point. And if you have that bad connection point, I'm talking the metal, the lug, to the bus, that type of connection point, if that is going high resistance, you will see a significant temperature difference there, and that can tell you that you have a problem with that connection point. In the termination itself, probably not so much would you see that with infrared. Probably the best way to predict an issue with a termination is one of the partial discharge tests, field partial discharge tests that are available out there. That can tell you if you're having discharge in operating voltage, and if you're having discharges at operating voltage, then that can lead to a failure for sure. Okay? Thanks.
Yep, that was going to be my last question. It came from Ted, who wanted to know, will partial discharge testing pick up potentially bad splices and terminations?
Yes, if done correctly, field partial discharge testing can pick up and detect issues with joints and terminations, and you know, potentially tell you that you can have issues with them. There's a lot of studies done on that, and if you're a member of NETRAC, you can get a copy of the studies that talks about partial discharge testing and field testing, and you know, the different methods that are out there, the pros and cons of them, and what they can tell you. So, and that's actually can be made available. If a hard copy can be made available if you are a member or not a member of NETRAC. So you just have to contact a member of NETRAC and give it and ask them for that information. But that's probably about the only way that I'm aware of that you can potentially determine if there's an issue with an accessory. So, okay, thanks. Thanks for all the questions. Thanks for participating.
Yep, thank you.
All right, anything else?